Welcome to PCI's Tech TV mini-series, Getting Started with Python and Geomatica. In episode 3 of our mini-series, we will create a quick script where we will chain multiple Geomatica functions together in order to automate a workflow that can be reused in the future. Since image orthorectification is a common process and is often required before imagery can be analyzed, it is a good task to automate with a simple script. Orthorectification is the process of ensuring every pixel in an image is assigned to the correct geographic coordinate. For this script, we require the same prerequisite Python knowledge as was required for the script we built in episode 2 of this mini-series. The most important thing here to remember is that Python executes code from left to right and top to bottom, so you need to call functions in the order in which they need to be run. The example in this episode will be to automatically orthorectify a single raw rapid-eye satellite image. We can see the rapid-eye image here. It's the small strip that's layered on top. And we're going to use the Landsat 8 image, which as you can see underlying, as a control source for automatic ground control point collection. What we want to accomplish here is quite simple. So let's just zoom into one-to-one. And if we toggle off the rapid-eye image, we can see that there is a shift here between the control source and the raw rapid-eye image. So the orthorectification process is basically the step of making sure that these two images will line up perfectly. Assuming we know the general steps required to orthorectify an image, we may need some guidance about which functions in the Geomatica library need to be run and in what order. For help with this, we will use the Geomatica Cookbook. For this, we can open up a web browser. And then in the Google, we can simply type in Geomatica Cookbook. So it should be the first result. And as you can see, it brings us to our cookbook page here. The cookbook is organized based on function area. So we can see here we have some options for general Geomatica recipes. We have satellite photogrammetry integration with ArcGIS, digital aerial photogrammetry, and other applications or function areas. So there's different recipes or blocks of code that are available in here for doing different useful tasks. In our case, we are interested in orthorectifying a satellite image, which falls under the category of satellite photogrammetry. So it is in this section that we should look for a recipe to see if it can help us in writing our script. Based on our understanding of the orthorectification workflow, we know that we need to first collect ground control points and refine them and then orthorectify the actual imagery. So we can look for recipes that may do this. So we can see that there is a recipe that does automatic GCP collection and refinement. So we can click on here and it brings us to a recipe where we have code that has been written for doing this as an example with a specific data set. So what we can do now is we can open up a text editor. So I'm just going to use Notepad++, and we'll just move these windows a little bit so it's easier to access. And then in this first section here, so we have the automatic GCP collection and refinement, we can copy and paste from the recipe. So we're just going to copy that, paste it into our document here, and we're going to begin working with this part of the code. So we can now save this text file. So we'll just go save as, just call it ortho.py, and now we have a color scheme that helps it makes it easier for editing the code. So the first thing that we're going to want to do within the editing of this code is to make sure that we point to the correct input imagery. And we can also change just the name of this variable. So that's for a GOI image. We're working with rapid-eye, but we can be more generic and just say raw image. We can then go to our desktop. So we'll just minimize some of these for now. And we can go to our input imagery. So we can see that we have our raw rapid-eye data is here, and we need to load the XML file. So we're just going to hold the Shift key down, right click, and go copy as path. And then we're just going to provide that path here. Then we need to know the output file that we want it to be written to. So this can be any file, but we're just going to put it back in our main project folder. We have already a folder called create or ingest GCP. So we'll just provide this directory, and then we'll just change the name of this to rapid-eye. But there's one more thing, is we change the name of the variable, so we also need to change the name of the variable here so that it's correctly mapped, because now we're passing this variable or this information into the link function. The next function that we're going to edit is the GCP collection function itself, called AutoGCP2. So we know that the near-infrared channel in our RapidEye image is stored in channel 5. So the reference image, the one where we're going to be using to collect the ground control points from, so we need to also point to this file. So we can just go to reference here. We have our Landsat 8 image, and we can just go shift, right click, and go copy as path, and provide that information in here. And then for this particular image, we stored the near-infrared channel in the band in the 4th channel. A next parameter that we need to update is the digital elevation model. So we have a DEM for our area. So same thing, I'm just going to go shift, right click. I'm going to get the path for that. Copy that in here. And then the GCP search radius is sufficient for our data. Another important thing to note is that we can see that when we call the function, we're making it equal to a particular variable. So we're calling it GCP seg. This is because AutoGCP2 function returns the output GCP segment in the PIX file where the GCP information is stored. So this is going to help us later on in our script when we want to identify which segment or where that GCP information is stored. So we can now go down to the next function, and we're going to set this one up. So it's the GCP refinement. This is the function which will remove the bad or blunder GCPs. So here we're going to edit two things. One, we're going to change the adjustment order to 1. This is because it makes the model a little bit less rigid. And we're going to also update this parameter. So we're actually going to give it a name and create a variable for it, which we'll just call it GCP seg refin. And then we'll add one over here, GCP seg refin. We're going to make it equal to an empty list. The reason we created that is because this GCP or this function GCP refin returns the output segment of the refined GCP information. So we need this when we want to continue on with our orthorectification process. So now that we've hacked this recipe in order to work with our environment, we can save this file. We can resort back to our Geomatica Cookbook. So we're going to go back to our table of contents. We're going to see if there's another recipe that does the rest of the workflow. So we can see we have an orthorectification with the GCPs previously collected. So this is exactly what we want. So here, once again, I can just copy this recipe, paste it at the end of our Python document here. I'm just going to move these import statements to the top. This is just good practice. And then we need to move on to modifying these last two function calls. So this first function that we just copied and pasted into the end of our script basically calculates the math model that is generated from the new GCPs that were collected. So we can modify this so we don't need the ingest directory because we already have that. We can just point to the link PIX file. And the GCP segment, we're just going to make that the GCP, the output parameter that's provided by the GCP refin function. And we can get rid of this line. So we're really just going to call, we already have all the parameters set up for what we need here. So the same thing is true with the last function that we're going to call, which is the actual orthorectification function, or ortho2. And we're just going to remove this folder here. We can point directly to the empty folder, and it's just going to write the file automatically and automatically name it. If we want, we can optionally provide a name for it as well, but in this case we're not going to. The DEM, well, we already have a variable up above that declares or defines our DEM, which is also called DEM. So it's already set here, so we can remove that. And then the map units we're just going to set to blank, as we'll use the default or input map units. So now that we have these parameters set up, the last thing we need to do is just verify that our arguments are correctly set. So we can see that this ingest dir is not a valid parameter to pass in our case. So what we want here is our input file. We can just go here and we can provide this. So the way that you know how to properly set these arguments is you just go to our online help, as you've seen here, as we showed you here. So this shows you how you pass arguments to the different functions. So finally, we can save this document and we can run it. To run this script, we're just going to bring up our command console. We're going to drag and drop our Python script that we created in there, and we're just going to click enter. So it's going to import all the modules, run the automatic GCP collection, collect the GCPs, and it's going to refine the GCPs. So we have sub-pixel accuracy, update the math model, and begin the ortho rectification process. Okay, now that the ortho process and the whole workflow is completed, we can take a look at the final results. So we've loaded the image in focus, and if we compare the original reference image to the new ortho image, we can see that we have a very nice sub-pixel alignment. Compared to the original raw image, you can see there was a fairly significant shift.